as Comet, Rift Volc, and the University of Bristol. And today I'm gonna give you some like a sample and different work that I've been doing. I'm gonna start by a brief introduction of the InSAR and what's the challenge of using InSAR as a real-time monitoring for volcanic activity. So I'm gonna give overview of the principle of radar interferometry, the advantages and limitation. And then I'm going to move on to two study cases. So the first one is going to be the analysis of ground deformation prior to the eruption of Agung in 2017. And the second one will be the analysis of topographic changes during the Fuego eruption in 2018. So I'm going to give each time a context, like the main result of the study, and also a discussion about what this study case can be applied to other places and what the involvement for like volcanology in general. So first, like the principle of radar interferometry. So I think if you're an expert in InSAR, that's the time to grab like a coffee and some snacks. I'm just going to talk 3-4 minutes for the people who are not familiar. So the radar interferometry uses the difference of phase between two paths, so the radar wavelength, and then you get a difference of phase that basically is a sum of different contributions, the flat earth, the topography of the area, the displacement, some atmospheric noise, and then some error. Then you have like for the radar interferometry, two different modes. So the first one is the repeat path interferometry, which is the most common one and used in many SAR missions. So the idea is you have two acquisitions of the same area at different time. And then if you are able to correct the topography using a digital elevation model, and you are able to correct some atmospheric noise using some correction, you may retrieve the displacement of the area. And here you see an example in Africa, in Suswa, that give you different fringes that's related to the ground deformation. So here you can count two fringes toward the satellite, and it gives you like a displacement in the line of sight. So this is like the basics of InSAR. And the second one is the bistatic interferometry. So it's less common. You have specific mission that would be static mode, such as the Tandem X. And here the idea is you have two acquisitions of the same area at the same time. So what's different here in the contribution of the phase, of the difference of the phase, is like you don't have deformation, neither deformation nor atmospheric noise. You only have some topography components and some error noise. So this is very relevant when you want to compute and have like a digital elevation model and derive a DEM using this technique. So this is a work that I've been doing in Congo in my past postdoc, where I was looking lava flows on Nyamulagira in the Virunga province. And I will talk about these techniques for the Fuego case. So what about InSAR and ground monitoring? So the advantages is you can perform day and night, it's cloud-free. It has a high spatial resolution comparing to ground instrumentation, and it can give you ground displacement over a large scale. So that's why it has been applied in many large regional surveys, such as in the Andes or in South Asia. And here is just an example of a work. It's like an ongoing project that I'm like working on at the moment, is looking the East African Rift, and you can just have a global survey using the last Sentinel-1 data and detect all the ground deformation in the different volcanic center. So it's a very advantage when, for example, in this area, you have a poor coverage of ground instrumentation. Of course, you have limitation, and the two main limitations I'm going to talk today is the atmospheric noise that you want to mitigate and correct, and the other one is the vegetation cover. So I will talk later about that. So we see like a very increase and growth of the number of radar missions we get from the last decade. So you can see like here there are like 7, 8 different missions, and we move from historical analysis when we were looking specific volcanoes or specific areas to now try to use this satellite data as a near real-time monitoring system. And to do so, there was a lot of initiative around different research teams that proposed some platform, some web portal that process automatically the radar in different areas. The idea is to provide ground displacement over like an earthquake or over like an active volcanoes as quick as possible as a monitoring tool. And then there is different initiative that you can see here on the right. And I'm going to talk just a little bit about LIXAR. So LIXAR is an automatic processing of Sentinel-1 data that's developed by the Comet, by my group. So the idea is having this automatic processing chain on the active tectonic region. So we started over the Alpine and Himalaya belt, and then we expanding over the Holocene active volcanoes, around more than 1,000 volcanoes. So you can really go to the website and check the different data that you see here on the left. So every activate frame, you can go and download like GeoTIFF of the different products, interferogram, and coherence maps. And there is a paper published recently by Lazeski that give you an overview of the system, how it works, the different products that generated, and the study we have been using. So what we are doing with this amount of data, so for volcanoes, we are looking toward an automatic detection for volcanic unrest. So here you see the flowchart. We are using the LIXAR automatic processing products. Then we are creating a volcano archive with different subset over the different 1,000 volcanoes. And we have now 500,000 of interferograms. So of course, you cannot check and have an expert checking all these interferogram over 1,000 volcanoes, and you need to develop tools that automatically detect if something is going on active volcanoes. And that's why we create with my group, Juliette Bix and Anna Straussy-Richai, machine learning techniques. So the idea is just flagging when there is ground deformation signal on an interferogram. And here you see on the lower right, an example in Galapagos that you see the RAP interferogram on the left and the flag signal here detected by the machine learning. So I'm not going to go into too much detail about the technique, but if you can have more detail, you can go through the publication and see for yourself. Now I'm going to start by the first study case, which is dike intrusion between neighborhood arc volcano responsible for the 2017 unrest at Agung in Bali. So first, a little bit of context. So the Agung volcano is located in Bali here in the Sundu subduction arc. It's an andesitic stratovolcano. And before the eruption in 2017, it has an eruption in 1963. So you can see here on the map that it's close to the Batur caldera. And it's interesting to know that during the 60 eruption, there was actually an eruption in February at Agung that was followed a few months later in September by an eruption in Batur. And the petrology seems to show similar magma similar composition of the magma between the two eruptions, with a mixing between basaltic and andesitic magmas. So going back to the 2017 seismic crisis, you can see here on the right the different timeline of the events. So we have a large increase of the number of seismic events during mid-September and a high plateau in October, before it decreased in mid-October to November and before the onset of the eruption. We see something quite unusual, that actually we have the start of the eruption that's not coincidence with the peak of the seismicity, but just a few weeks later. If you look at the location of the event, so because of the different station, the small amount of station is difficult to have a precise location. So what we are looking here on the left is just some density of events during the seismic swarm. And what you can see is like clearly an offset. So there is a seismic swarm that's located right in the middle between Batur and Agung volcano. And the density here is higher, like so right in the middle in this line between the two edifices. So the seismic swarm seems offset from the central edifice of Agung. And this is interesting because this distal seismic swarm is something we see on other like arc volcanoes. So we see here in Pinatubo or Unzen or Cerro Negro that they are often, but not always, precursor of volcanic eruption. And the peak seismicity correlates generally with the eruption onset, but it was not the case, for example, at Agung volcano. So the idea and the importance here was to know what caused this seismic swarm during the seismic crisis. And you can think about two mechanisms. The first is a distal event on fault due to stress transfer. So you have a central magmatic system that's pressurized and triggers some fault nearby. The other is to think about offset in the magmatic system, and that you have actually the seismic swarm that's related to propagation of magma away from the central edifice. So how you can try to discriminate between these two scenarios? You can first look at the location and focal mechanism of seismic events, the pattern of ground deformation associated, or to map the tectonic structure and see if the seismic is located nearby a tectonic structure pre-existing. The problem here is the seismic quality, or the quality of the seismic data were not enough to do some study about the focal mechanism, and the mapping of tectonic structure is very poor in the region due to small amount of historic eruption and earthquake. So the pattern of ground deformation was really a key data set to really understand and discriminate between these two scenarios. So what we did is look at the Sentinel-1 time series and see if there is ground deformation associated to this seismic swarm during the 2017 event. We want to answer to this question. So which magmatic source was active during this event? Which mechanism is driving the 2017 seismic swarm? And is there any magmatic connection between Batur and Mont Agung, which was suggested maybe during the 1963 eruption? So we are using the Sentinel-1 mission that was launched during June 2014. And here what we have is we're going to have a difference of phase that's sum between the atmospheric signal and ground deformation signal. And this is very key and challenging for this kind of volcano that's located in tropical region. So here you see a picture of the Mont Agung. As I said before, you see very strong variation in the atmosphere close to the summit. And then you have on the right an example of an interferogram that was processed during September 2017, and you see clearly some fringes on the summit. So key question is like, is it deformation or atmosphere? And it's very key and was very challenging during the seismic crisis that this kind of open access data and Sentinel-1 that can be processed by anyone was published on social media and end up with having a negative impact in the management of the crisis. So I think there is a responsibility of the scientists and the community to really be careful when there is an interpretation of this kind of individual interferogram, as they can be misleading for non-experts, of course. So what we need to do first to be sure that it's deformation or not is to look at the atmospheric phase signal and try to correct them. And so what you need to know here is the atmospheric signal is a component, is a sum of two components. The stratified component, which is mostly correlated with elevation, and that will give like fringes, concentric fringes that correlate with topography. And then a turbulent component that's supposed to be random in time and space. So the simple method that was developed like in the past was to use empirical method based on the phase elevation correction. The only problem of this type of correction is that they only correct one part of the signal. Then we move on to some other type of correction that use external data sets that can both correct stratify and turbulent components using some spectrometer data set as MODIS and MERIS, some GPS zenith tropospheric delays, or weather model. And what we were using during the seismic crisis at Agung is actually some weather model based on the ECMWF high resolution weather model that give atmospheric delay maps every 6 hours. So this is produced and developed by the University of Newcastle via the GACOS online system. So here you see an example of this, the same interferogram I show you here on the raw interferogram on the left, the GACOS atmospheric model on the right at the same time acquisition, and then the correction and the corrected interferogram on the right. So you clearly see that these fringes that we've seen before here on the summit were actually only atmospheric signal, and there is no remaining deformation when you correct them. So the idea is to do systematically this correction and try to have a better idea and a better detection of the ground deformation. So here I will show you just some example of different RAP interferogram and their associated correction. So here you see an interferogram with a large positive signal here on the coastline. And you can see that the Gaco's correction do a pretty good job by removing this turbulent atmosphere that's along the coastline. Whereas the phase elevation correction only give you some correction for the summits, but never able to retrieve this kind of turbulent noise on the coast. So you clearly see like the relevance and the better quality of the Gaco's correction for this kind of signal that you want to correct. Here I show you another example when you have an atmospheric signal that's more subtle, that's more small, and that seems to be only located here on the summit on Batur and Agung. Here you see that the Gaco's correction do a good job to have the trend, so the positive, kind of the global shape of the atmospheric signal, but it will overcorrect here on the corner. Whereas in the phase elevation correction, you see like a better correction that only give a positive signal for high elevation. So what we did and what we show in this paper that published recently in 2020 is that you have to combine and you have to actually use an hybrid method that take the advantage of both Gaco's weather model-based correction and phase elevation correction to retrieve and to remove most of the atmospheric signal you get on the data, and especially for these tropical volcanoes. So what we were doing is a quality assessment through the whole data set. So you can see here the percentage of reduction of the standard deviation. So you are looking the difference between uncorrected and corrected, the relative difference, and estimated as a function of the standard deviation of the row interferogram. And for the Gaco's correction, you clearly see a trend. So when you have a strong signal, as I showed before, it's the corrector is more efficient. And then when you decrease and have a small signal on the interferogram, it will be difficult, and even you're going to introduce noise in your data by having negative reduction. As you see on the right, the phase elevation only have high quality for specific date. And this is due because only these data have more stratified components. So there is no trend, no correlation, is only specific time, specific date that will be better corrected by the phase elevation correction. So we did this quality assessment for this volcano, and now we try to expand and look at other like volcanic environment, such as Turkish volcanoes, and try to apply the method I developed for this work to other places to see how it works. So now we did some stacking of the corrected interferogram after we removed the atmospheric signal, and we look at two periods. The first from mid-April to August, we see like no clear ground deformation on the valley. Whereas if you see the period 2, which is between August the 1st and November 21st, so during the seismic crisis, you clearly see a positive displacement, so an uplift of the flank of the volcano in both ascending and descending. So we are quite confident that this is a real ground deformation signal, which is a wide uplift of 8-10 centimeters. And if you look at the time series to see how it correlates with the seismic swarm, you can clearly see if you don't correct anything, you get noise, and you cannot discriminate any, you cannot detect any deformation. Whereas when you have this corrected time series, you see this step, this ramp of the displacement in both ascending and descending. And the last thing we developed is to actually try to do, use some anomaly detection. So the idea is to, as a monitoring, to detect as early as possible when you get something unusual, something that looks above the noise of your data set. And we developed this QSUM approach, which is just a sequential analysis used to detect anomalies in a time series. So it just detects everything that's diverged from the mean. And you just see here that at the time here, when you see in the gray shade area, which is the seismic swarm, you detect an anomaly in both ascending and descending. So you can be sure that during this October, when there was a seismic crisis, there was a large anomaly due to the ground deformation. And then you can implement that in a volcano observatory to do it kind of in a near real time. So now that we have this ground deformation signal, of course, the idea is to better understand the mechanism and the source of the deformation. So we use finite element modeling, 3D finite element modeling that consider the topography. The medium is elastic, homogeneous, and isotrope. We test different geometry for the source, but the best source we had during the inversion is a magma intrusion with 8 parameters. And I show you here the results. So here, this is the interferogram. This is the best model, the best fit model, and the residual. So we see actually that the ground deformation can be explained by the emplacement of a dike intrusion here that sits right in the middle between Batur and Agung with some different characteristics. But the most important thing is to see the position of the dike, which is right in the midway between the two edifices. Then we can do something a little bit better by looking the incremental volume change. So the different volume change at different time steps. So here the data show you the deformation and the inversion. So we keep constant the geometry and look inverse for the volume change and see here that you have an exponential decay, a volume change that you can see here, the different dates now here that correspond to the decay of the seismicity. So at the same time that you have this high increase of seismicity in this plateau, you have an emplacement of a dike with a large volume increase. And then when the seismicity die out and decrease, the number of events dramatically decrease, you reach kind of a plateau and an asymptotic limit here. We can also see that the last dates seem very offset from this exponential decay. And we believe this is something real, this is a real mechanism, and it's not can be accounted by the uncertainties. So we believe that something happened between these two dates and before the eruption, that maybe the intrusion interact with a shallow magmatic system, and the volume change really dropped at that time. So if we summarize all this funding with the ground deformation data, we can see that there was a magma transfer from deep source into a dike intrusion that in place midway between Batur and Agung. It was like simultaneously with the occurrence of the seismic crisis. So we can really reassure that the seismicity was caused by magma intrusion. And then something happened. We don't have any clue about the shallow magmatic system that maybe interact with the dike intrusion just before the eruption. We don't see any signal related to this shallow source. But we can think about a mixing between this intrusion and the shallow source that may have triggered the lash push for the eruption. So if we make a summary for this study case, we can say that which magmatic source were active during the crisis. It was a deep dike intrusion that was located midway. The mechanism of the 2017 seismic swarm was due to the magma propagation and not a stress transfer on a fault. And this really posed the question about the magmatic connection between Batur and Agung, because it seems that part actually of this magmatic system may be offset from Agung and can contribute both to an eruption in Batur or Agung in the shallow part of the system. And what about the implication for other volcanoes? I think there is a very interesting point here to look at more the simultaneous eruption at other stratovolcanoes. So there was already the case for some Kamchatka volcanic system. And moving from the concept of central magmatic system and look at more in statistically the offset of magmatic system. And this has been already done by recent studies by my colleague Suzy M. Meyer or Lerner at the University of Oregon that look statistically how a magmatic system can be offset from the central edifice, and they found both the same result, about 20%. So it's very interesting to see how this system evolve in time and in space. I think, yeah, further study needs to look at different study cases. I'm now move on to the second study case that using tandem X to measure pyroclastic flow, source location, thickness, and volume. So here is a study about the Fuego eruption in 2018. So the interesting here is look at this eruption and how we can better the forecasting of pyroclastic density currents. So we all know that pyroclastic density currents is a common hazard during explosive eruption. It has a high human cost. So you see here is about 33% of the fatalities. And the Fuego eruption was one of the cases for the 21st century and has been reported as the deadliest eruption for this century. Number of fatalities went from 300 for the number from the authorities up to 2,900 from some independent reports. So quite a big impact for this eruption on the population. And of course, this eruption have a high economical cost due to the evacuation of the population. So why forecasting of pyroclastic density current is important and how you do it. First, you need to understand from one side the flow processes. So you can collect historical records from the different eruption of the volcano, a collection of observation, runout distance, thickness, and then an important work on the simulation of the flow. And the simulation of the flow and the combination of all this information give you a better idea of the hazard maps, the evacuation zone, and of course has an impact of the risk assessment you're going to do for this volcano. So what we did during this study is to use tandem X bistatic interferometry to produce a digital elevation model after the eruption of 2018 at Fuego. So as I said before, in this case, we can retrieve the topography because of the bistatic mode. There is no atmospheric noise or deformation in the difference of phase for the interferogram. So it's very relevant for producing high resolution DEM. The limitation we have with this technique is using the tandem X using X-band wavelength, and the X-band is affected by the vegetation. So what you're going to have is not a surface of the ground, but you may reflect the top of the trees. So sometimes your digital elevation may be a model of the vegetation rather than the bare earth in the ground. So you need to be aware of that. The tandem X data have been used a lot for lava flow thickness. So here is just a sample of different examples in Kilauea, Piton La Fournaise, one of my work in Yamulagira. So you see this lava flow thickness with a very high resolution, spatial resolution. You can have a thickness information in each pixel. So it gives you a very accurate information about the volume, the total erupted volume, and also where it was used to derive mass flow, for example, in Hawaii. Why it has been used a lot in lava flows is because the topographic changes associated to lava flow is very easy to detect. So here you see a picture of the Hawaii eruption, and you have here the edge of the flow. So you can really see the difference between the non-affected area, non-impacted area here that will have no topographic changes, and here the lava flows then in place, and that will give you a strong topographic change. When you look at pyroclastic density currents, pyroclastic flow in general, will be more difficult to really discriminate the different processes about topographic changes that can be due to different mechanisms. So you have very small ash fall, thin ash fall on some parts, the removal of the trees that's going to affect the topographic changes, surge deposits here on the overbank, and flow deposits. So it's a combination of many processes, and it's very difficult to retrieve the thickness. And this is why it was not applied in this explosive eruption. So we tried for the first time on the Fuego eruption. Was on June 2018, an explosive eruption with large pyroclastic density currents. As I said before, very deadly eruption. And one of the interesting features of this eruption, if you look at the flow map here, is that it reached up to 12 kilometers, whereas during the cycle between 1999 and 2017, PDC reached about 6 kilometers So there was kind of a interesting event and compared to the previous one. And our colleague Elsa did a very nice study to look at this eruptive cycle and all these different eruptions. One important point here also was the difference between fatalities in different regions of the flow. So here, comparing the La Réunion Gulf Resort, which is a Gulf resort located here around 6-7 kilometers from the summit, there was a high awareness and evacuation on time with no fatalities, whereas in San Miguel Los Lotes, that's a further 2 kilometers on downstream, you had a low awareness with maybe a lack of willingness that contribute to a late evacuation and high human cost. And yeah, our colleague published recently this a nice study about the perception of the local population. She did interview on 32 interviews and look at the awareness in different parts of Fuego on the flank to understand why there was this difference, spatial difference on evacuation during this event and how to improve that. So the first thing we did was actually to look at Sentinel-1 optical imagery to identify the different facies of the flow. And we identified 5 different facies: collapse, transitional, ash cloud surge, overbank, and channel. So this allows us to map and have different facies and to look at these facies, how is the topographic changes in all the different facies. So here you see the first tandem DM difference post-eruptive. So I'm looking different date after the eruption, and you expect that there is no topographic changes. So here you see the map of the flow, the outline of the flow, and the distribution here show you that here on the reference area outside the flow or inside the flow, the distribution is quite the same, center on 0. So it's kind of a reference to see that the method is accurate. So we see that after the eruption, if you look at them difference, there is no significant topographic changes. If you look now the co-eruptive DM difference, we see another picture. So first, what you can see is kind of a negative topographic changes here on the proximal section, whereas you see some positive into the channel here in the distal section. And if you look at the distribution inside the flow and compare to the reference area, so you see here this negative topographic changes that could be due to erosion or collapse, and here some positive due to deposition. So what we look is the different sections. So here I'm going to start with the distal section and try to compare the topographic changes we have with the different facies we mapped with Sentinel-2. And here what you can see is a very good, the result very concordant. So you see these positive changes here on the channel, on the main channel, whereas you see negative changes here on the vegetation. So all the overbank that has vegetation, you clearly see this negative. And when you do a profile, you have the transition of positive change, so deposition on the main channel, and then some negative changes on the overbank. And what we believe here is that what we see as a negative changes is actually because of the trees. So before the eruption, you have this DM that model the top of the trees, and after the eruption, due to the pyroclastic flow, you have destruction of the trees, removal of the leaves, and the scatter is lower, and then you see these apparent negative changes. So we clearly see an impact of the vegetation on the results, shown as negative topographic changes in all the overbank. Then if you look at close to the summit, so this is a proximal section, you see here during the eruption, negative topographic changes all around here, about 1-2 kilometers along. So you see these negative topographic changes and you ask yourself, okay, is it a real mechanism? So then you look some pictures before and after the eruption, and we see that it looks agree with the photo that you see here, a very collapse of material, the volcanic materials in the summit of the volcano. So we believe that what we see as a negative topographic change is actually a collapse of part of the summit here. And we look at post-eruptive and pre-eruptive DM difference. So if you look at the post-eruptive, you see that there is no topographic changes. So we are confident that this is a real signal. But the more interesting thing is, like, if you look at between October and 2015, the 18 and 29, you see again this kind of negative topographic changes here on the proximal section. And it was actually during a small eruption. So it was an eruption with a less intensity than the 2018 eruption, but still this small eruption may have triggered some collapse on the summit of accumulation of materials. And this is what we see when we do the profile along this. We see some recurrent about 30-meter collapse in this area, in this proximal area. So we believe that is not something that's only occurred during the 2018 eruption, but also in the past, even when there is a small eruption that shake the summit of the volcano. So then we look at the mass balance and the total volume for the positive, for the deposition, and for the negative. So for the negative contribution, we divide between the erosion and the vegetation contribution. So if you look at only the balance between the volume of deposition and the total volume of erosion, we see a kind of similar order of magnitude. So we believe here that we are detecting a bulking effect. So this is the class incorporation process that increases the flow volumetric solid fraction. So most of the volume that deposit in the distal section come from this collapse and this mass removal at the summit. So this was some evidence of this bulking effect was shown in the Tungu area 2006 eruption on an outcrop. But here we clearly see a bulking effect at the scale of the flow. So with this technique, we are able to really quantify this phenomenon. And if you like, look at the volume per facies, so what I show here is for all the different facies, from proximal to distal, the deposition, and in dark blue, the erosion, you see kind of an increase of deposition from proximal to distal, whereas at the same time, you see a decrease from proximal to distal from erosion. So at the same time, you have this mass balance between erosion and deposition. And one interesting thing is to try to understand at which slope value this transition occurs. So which slope you have the transition between these two phenomena. So we looked at the mean slope for each different facies. And here you have a plot that shows you the net volume as a function of the slope in degree. And you see the proximal facies here in blue with a transition to distal and deposition about 20 to 29 degrees. So this is consistent with previous result. We report here a transition between collapse eruption at Fuego around 20-29 degrees between erosion and deposition. And we are able to do it as a scale of the flow rather than just at outcrops. So to wrap it up, the conclusion of this study, for the Fuego eruption, we show that the bulking process contributes largely to the total volume of the 2018 PDC. It had increased the flow mobility, which could explain this increase in runout distance, so why we reached 12 kilometers and not 6 as previous eruptions. We see that collapse events at the summit are recurrent phenomena and was detected before during the 2015 eruption. And for the application of other volcanoes, I think it's an interesting study, very important to show that Tandem X is also has the capacity to monitor accumulation, collapse of volcanic material at stratovolcanoes. So it could be applied to other stratovolcanoes. And it's also a good tool for the validation of numerical simulation and also to build next generation modeling of PDC that take into account this bulking effect at the summit. For the general conclusion is perspective. I think I show here the benefit of weather-based atmospheric correction for detecting ground deformation for the volcanic crazes for Agung, that there is a need for systematic correction using weather model on the global scale with the implementation, for example, of GACO's correction for the InSAR automatic processing. So it's something we are working on. the benefit of this static InSAR to detect the thickness of pyroclastic density currents for the example of Fuego eruption. And in the future, the need for monitoring more like the mass accumulation and collapse on stratovolcanoes. And hopefully the future radar missions such as Tandem-L will be a great data set to test this. Okay, thank you.
Thank you, Fabien. That was fantastic. Great applications there. So we have time for questions and discussion. And so go ahead and raise your hand. It looks like we have several questions, actually a couple questions at least on the atmospheric correction bit. We'll start with Mark's question first. And if another question comes to you, feel free to use the raise a hand function. So I'll read Mark's question, and you can also see it, Fabien, I think. In your corrections, is the phase delay related to atmospheric stratification related mostly to the wavelength of internal gravity waves?
So yeah, so we haven't looked in detail the wavelength, like how it reports to wavelength of internal gravity waves. What we see for Agung is mostly so the large signal we see on the coastline seems like recurrent. So this large wavelength that can be corrected with geckos on the coastline look kind of a recurrent signal that we are able to identify. For the stratify atmospheric, so the stratify component that we see on Agung is more difficult to really have a kind of better idea if it's or not related to this small wavelength of gravity waves. Yeah.
Then there's actually, I think, a somewhat connected question from Victoria, and she asks, for the combined atmospheric correction method, does this mitigate any overcorrection from the geckos? Further, she writes, I'm not sure if you are just applying both methods or a separate method, which is some compromise of geckos and a linear correction.
Yeah, so that's an interesting question. So I've been doing some tests, and in the paper I mentioned kind of the most efficient correction. So the approach I did is not to choose for each interferogram what's the most efficient between the geckos and the phase elevation correction, because if you are doing that on an on a daisy chain, you may end up with first correcting the geckos correction for image 1 and image 2, and then not correcting for the second one and get some residual, high residual. So I test different method, and the most efficient one that I apply is actually use first the geckos correction as always to correct the interferogram, and then look at if there is some overcorrection and apply like a linear ramp to remove this overcorrection, and then use the phase elevation if needed, because we also know that if you have a ground deformation on the summit of the volcano that be correlated with topography, you may remove the signal by applying empirical method. So the empirical method is kind of the last step at the end. If there is some high at the scale of the Bali island, if there is still some phase elevation correlation, I apply finally. So it's like a two-step. Is not choosing the best method of two, but it's more applying geckos correction, looking some residual in the overcorrection, and then applying the phase elevation at the end if it's needed.
Since we're on this theme, I actually had a question related to this topic too. And I know you would have this in many places, but in populated areas, sometimes you can get meteorologic soundings from balloons. Is this something that would be useful to add as an extra correction or extra point data, especially when you're dealing with global climate models that have trouble near topography and
so that will be good. I think it depends. If you have this external data set, I think it's worth to use it and to add this extra information. Not sure in Indonesia, in Bali, you get such a data, but we clearly show in our study that there is a problem with Gecko's data on the high elevation, because Agung is very typical, is above 3,000 meters, and is the only mount in Bali that has such a high elevation. So actually you cannot correlate it with high elevation in other parts of Bali that should have kind of the same stratified atmosphere. So it's kind of interesting way to, and I think this is the way we want to move on from Gecko's data, is try to refine, because of this issue, the information on high peak and high stratovolcano, of course. Yeah.
Thanks. Francisco has a few questions here. We'll start with the first, I guess. The Agung deformation is large enough to be detected by L-band data. So did you attempt some ALOS2 interferograms?
I think during the crisis, Paul Lundgren did some ALOS, and we had some ALOS interferogram, I remember, during the seismic crisis at that time, that were showing also kind of the same signal, especially on descending track, I think. So we were looking also ALOS data at that time. It's not on the study, on the work I have published, but it definitely show up on ALOS data. Yeah.
Yeah, and I should say, Francisco, feel free to unmute yourself if you have follow-up things to these questions too. I'll move on to Francisco's second question, which is why is there a delay between the dike intrusion and the eruption?
Yeah, that's a good question. Like the final timeline of the eruption is very, I think there is multiple hypotheses. We don't have a very, let's say, final answer to that point. So what I show is like the seismicity decrease, the number of events decrease, the dike volume increase, like decay. So we believe that there is a stopping in the propagation of the dike that caused this decrease of seismicity. And the interpretation we have is maybe a mixing between the dike, because we saw, as I show in the composition, there is magma missing definitely in Batur and Agung during the 1963 eruption. So with basic, more mafic and andesitic. So why not having this residual magmatic system at shallow depth? Unfortunately, we don't see any evidence in ground deformation that of this shallow system. It could be that the magma is so compressible that the volume change doesn't induce any deformation at the surface. And we are central now to, I mean, if it's a central system to Agung, we also have to consider that because of atmospheric stratified components and this high component on the volcano, the accuracy, I mean, the uncertainties on this area is higher than elsewhere. So we might miss the signal, or the signal is not there because it's compressible magma. I think that's kind of the two answers I had here.
Yeah, thank you. And then lastly, Francisco writes, for Fuego, did you try some Pleiades DMEM, or do the clouds hinder the use of optical DEMs in tropical areas?
No, I haven't. We haven't checked Pleiades DM. I think, a lot of cloud, lot of Pleiades DM in this kind of volcano are kind of not easy to use. So yeah, we haven't looked this Pleiades optical DM. I think the TONA do a pretty good job with this kind of DM difference and deriving thickness. But yeah, it's something to look at for other places, I think.
Let's see. Lots of, and so also, I should say, Fabien, on the recording, you'll also have a copy of these. So there are lots of nice comments here too. Let's see. I think that covers the questions that have been asked in chat. Does anybody else have a question or two they'd like to ask just by raising your hand? I guess I just have a question in terms of the PDC work, which I found really interesting. In terms of getting the DEM product, from a satellite pass to the DEM product, what's sort of a realistic sort of timeline for that to operate on?
So yeah, it was a very interesting. I mean, we have a small discussion on that on the paper because yeah, we had there was quite a delay when there was a fast response to the volcanic crisis that University of Bristol was involved in with the volcano observatories to get as quick as possible a DM, but we see some delay on the Tandem X data because of the DLR and the request. So they had to request, of course, the area. So I think we estimate that there was, I think, between the eruption and the moment that we get the raw data was already 2 months or something. So in that sense of getting like near real time and having an update as quick as possible in the days or weeks, we were not able to do it with this Fuego case. And I think it's something we want with Juliette Bix and with the group is for future mission, radar mission, the Tandem L, or mission that will provide some data that's relevant for digital elevation model to be produced, kind of really reduce this time between the moment there is a request of the data and the moment you can really generate your DM. Because after the generation of the DM is a matter of a day and 2 days, and you can automate the system to get this DEM difference. So yeah, I think it's the main point in pushing the mission, the future radar mission for that's gonna produce or give us data to do DM.
Thank you. Okay, well, any last questions? Fabien, if you have a couple seconds here, we'll probably just let everybody else close out. And but if you have a question you'd like to ask Fabien kind of in a smaller setting, maybe you could stick around for a couple minutes and ask Fabien in a small group that kind of sticks around for a minute or two.
And if you are shy, just you can also send me an email and question on my email. I will be happy to answer that too.
Well, thank you so much, Fabien.
Thank you, Brian. Thank you for the invitation and for this this webinar, and thanks everyone that listened me.
Great. Well, join us next week, and we'll see everybody soon.